Hello, welcome to this video tutorial on measures of variability. This video will have the objectives to find the interquartile range, the semi-interquartile range, mean deviation, and standard deviation of a set of data, then to organize and compare the data using box and whisker plots. So let's begin. Here we have a set of temperatures for a town. And we are going to break it up to find the interquartile range of the temperatures and the semi-quartile range of the temperatures. So let's begin with the interquartile. The first thing we want to do is put these data points in order from least to greatest. So I've got that here. Now, I will take this and I have a total of 15 temperatures. So I'm going to cut this in half, which I count 1, 2, 3, 4, 5, 6, 7 right here. This is my median temperature. Okay? This is the median. Then I will cut each of those halves into halves, thus giving me quarters. So that will happen right here, and it happens right here. This, in essence, gives me the end of the first quarter, so that's quarter 1. The end of the second quarter of the data, quarter 2. The end of the third quarter of the data, quarter 3, and also known as the first, second, and third quartiles. Okay, so then the semi-interquartile range. So I begin by finding the range of the inner quarters, okay, which are the end of the second quarter and the third quarters. So 65 to 73, that's a difference of 8. And so I'm going to do semi, which means half of that. So I will take half of that 8 degrees, which is 4. So I have an interquartile range of 8 and a semi-interquartile range of 4. Okay. Next thing we do, we are going to draw a box and whisker plot of the data. So I've already done a lot of the legwork for this by putting everything in order and marking off the quartiles. What I want to do now is place the lower value, the upper value, along with the quartile marks on a number line. Okay? So that looks like this. And I take that end of the first quartile, second quartile, and third quartile, and I place vertical lines on them and draw a box around them, thus creating the box. So then creating the whisker part, I actually have, a lot of people will just go ahead and draw lines out to those outer points. But before you do that, you need to actually determine if there are any outliers. Now, an outlier is a value that by common understanding is 1.5 times the interquartile range. So 1.5 times, in this case, 8, because remember we found 8 was our interquartile range. So anything that is 12 degrees above our upper third quartile or 12 degrees below our first quartile. So 12 degrees below 65 would take us all the way down to 53. Now this bottom point is at 60, which is not beyond 53, so that's okay. I can go ahead and connect that with a whisker. 12 degrees above the third quartile would take me up to 85, which this upper point here, as we refer back, was at 81. It's not beyond 85, so that's okay. I can connect this as well. I have no outliers in this. Again, an outlier would be 1.5 times the interquartile range beyond the first quartile and third quartile marks. Okay, so, all right, let's keep moving. Referring again back to that first data set, find the mean deviation of the temperatures. Okay, so mean deviation is a little different than standard deviation. we have to note the average first. So I add up all the temperatures and divide by the 15 values, giving me 69. And then to find the mean deviation, I take each of the values, subtract from that the average, the mean, take the absolute value and I add all of those up, and then divide by 15. Now let me go into a little bit more detail on what this part of it entails. So I take each of the values here. I'll start maybe with my first one, 60. And I go 60 minus 69 is negative 9. Absolute value, that's 9. So I go 9 plus, and I go to my next one, 62. So 62 minus 69 is negative 7. Absolute value is 7. And then I continue that on, adding them all up. And then once that's done, I divide by 15. So the sum of all those absolute values of the differences is 71 divided by 15 is 4.73. That is what we call the mean deviation. The next one, we're going to find the standard deviation, which is a little bit different. There's two big noticeable differences. I'm going to take, instead of the absolute value here, I actually square the difference. Okay? So we'll see that here. Instead of the absolute value, I square the difference. And then after I divide by the 15, I take the square root. Okay? So for instance, that first temperature of 60 degrees, I go 60 minus 69 is negative 9, squared is 81. The next one, 62. 62 minus 69 is negative 7, squared is 49. So 49. And I keep adding all those up, divide by the 15, and take the square root, and we get 5.6. That is my standard deviation. Now, standard deviation can be thought of as what is a typical range, okay, off of the mean. So in this case, I would say the temperature in this town is 69 degrees, give or take about 5.5 degrees or 5.6 degrees. So I wouldn't be surprised to have a temperature of 74.6 degrees or as low as 63.4 degrees. That would be within one standard deviation above and below the mean. Okay, the next thing we're going to do is use a frequency distribution data table to find the arithmetic mean, also just referred to as the mean or average, and the standard deviation of highway speeds for 50 vehicles. So on the table, I've got the data broken into class limits, and the class marks, which is the midpoint of the limit, and then the frequency of each of those classes. All right, so the first thing we need to do is to take the frequency and multiply it by the class marks, which gives us an approximation of the sum of all the values in that class. Now, this is an approximation, we don't know exactly, but it is acceptable for our uses here. Okay? So I would expect if I added up all the cars in the 50 to 60 mile per hour range, that if I added up all their speeds, they'd come out to 330. And that's 6 times 55. And I do that for each of the class limits, and I add them together. That allows me to find the arithmetic mean. I take the summation of all the speeds, divide by the 50 vehicles, and that gives me a speed of 69.4 for my average. Now, for the standard deviation, if we look back at our formula, I'm going to need to take the difference of each of those speeds and the average. Okay, so that's the first thing I'm going to do. Now this is the class mark minus the average. Okay, 55 minus my 69.4 is what I'm doing here. The class mark minus the average. And then I'm going to go ahead and square that, because that was the next part in the standard deviation, is to square that. And then I say that that difference happens 6 times. So I'm going to multiply that by my frequency. So I take that squared difference and multiply it by 6 to get 1,244.16. Okay? And I do that for each of my classes and add them up, because that's what the standard deviation asks us to do is to find that summation. So we add it up, and then I'm going to have to divide by the number of vehicles, which was 50, and take the square root. Okay, so that's what I'm going to do. We take the summation of those, which is 3,832, divide by the 50 vehicles and take the square root, which gives me a standard deviation of approximately 8.75. So I would expect typical speeds to be within 8.75 miles per hour of the average 69.4 miles per hour. So above or below this average by 8.75. Okay, there we go. I hope you found this helpful. Keep persevering in your study of mathematics. Good luck, and I wish you well.